Hello friends. Welcome to my YouTube channel Chemical Adda. Please watch this video till the end to learn about the Ponchon and Savarit method. In this video, we will discuss the second part of the Ponchon Savarit method. In the first part of this video, we have already discussed how can apply the Ponchon Savarit method to the rectifying section. Now, in this video, we will discuss the next part, which is the Ponchon Savarit method for the stripping section. So, first let us write material balance and component balance equation for the stripping section or envelope 4. For any M tray, the total material balance can be written as L-M is equal to G-M plus 1 plus W. And the component balance can be written as L-M into XM is equal to G-M plus 1 into YM plus 1 plus WXW. Where L-M is moles of liquid, leaving M tray per unit time, of composition XM. G-M plus 1 is moles of vapor, entering M tray per unit time, of composition YM plus 1. And W is moles of residue, per unit time, of composition XW. Hence, after rearranging the term of equation 2 can be written as L-M into XM minus G-M plus 1 into YM plus 1 is equal to WXW. Where the left-hand side of the equation 3 represents the difference in the rate of flow of component A, which flows from down to up. So, basically, it represents the net flow of component A in the downward direction. But the right-hand side of equation 3, WXW, remains constant for the specified distillation. Because WXW represents the rate of permanent removal of A from the bottom, and which is constant for the specified operation. And this difference is independent of the tray number within this section of the tower. Hence, from this, we can conclude that the difference or net rate of flow of component A in the downward direction is also constant. Now, let's write the enthalpy balance for the stripping section. Hence we get L-M into HLM plus QB is equal to G-M plus 1 into HGM plus 1 plus WHW. Where HLM is the specific enthalpy of liquid leaving the M tray. HGM plus 1 is the specific enthalpy of vapor entering the M tray. HW is the specific enthalpy of residue. QB is the amount of heat entered at the reboiler per unit of time. Hence, after rearranging the term of equation 4, it can be written as L-M into HLM minus G-M plus 1 into HGM plus 1 is equal to WHW minus QB. Now, let us assume Q double dash as a net flow of heat outward from the bottom of the column per mole of residue. Hence, Q double dash can be written as Q double dash is equal to the heat removed in the residue minus heat entered at the reboiler divided by moles of residue. Hence, the formula for Q double dash can be written as Q double dash is equal to WHW minus QB divided by W, which can also be written as HW minus QB divided by W. So, after rearranging the term, this equation can be written as WQ double dash is equal to WHW minus QB. Now, by comparing equations 5 and 7, we get L-M into HLM minus G-M plus 1 into HGM plus 1 is equal to WQ double dash. Where the left-hand side of the equation 8 represents the difference in the rate of heat flow from downside to upside. Or we can say it represents the net rate of heat flow in the downward direction. But the right-hand side of equation 8, that is WQ double dash, remains constant for the specified distillation. Because the WQ double dash represents the constant net rate of heat flow from the bottom for all trays in this section. Hence, from this, we can conclude that the difference or net rate of heat flow in the downward direction is also constant. In this manner, we get 3 equations for the stripping section. Now, from these 3 equations, let's find out the equation for L-M divided by G-M plus 1. So after rearranging the term of equation 1, we get the value of W. Hence equation 1 can be written as L dash M minus G dash M plus 1 is equal to W. Now let's put the value of W from equation 9 in equation 3, hence we get. So, after solving and rearranging the terms, we get L dash M divided by G dash M plus 1 is equal to Ym plus 1 minus XW divided by Xm minus XW. Similarly, after putting the value of W from equation 9 in equation 8, we get. After solving and rearranging the terms, we get L dash M divided by G dash M plus 1 is equal to HGM plus 1 minus Q double dash divided by HLM minus Q double dash. Hence, after comparing equations 10 and 11, we get L dash M divided by G dash M plus 1 is equal to Ym plus 1 minus XW divided by Xm minus XW, which is also equal to HGM plus 1 minus Q double dash divided by HLM minus Q double dash. Hence from the material and energy balance equation, we get the equation for L dash M divided by G dash M plus 1. So this equation shows the equation for a straight line on the HXY, that is enthalpy, and XY, that is composition diagram. Such that, on the enthalpy diagram, this equation shows a straight line which passes through the points HGM plus 1 Ym plus 1 at G dash M plus 1. HLM-XM at L dash and Q double dash XW at delta W, where delta W is a difference point whose coordinates represent differences in the rates of flow, such that Q double dash is equal to the difference in heat flow from downside to upside divided by net moles of the total substance out. Or we can say that Q double dash is equal to net heat out divided by net moles out. And XW. XW is equal to the difference in the flow of component A from downside to upside divided by net moles of total substance out. Or we can say that XW is equal to moles of A out divided by net moles out. But delta W is a fictitious stream in amount equal to the net flow outward, such that delta W is equal to L dash M minus G dash M plus 1. Similarly, equation 12 also shows a straight line on XY or composition diagram, which is passing through the points Ym plus 1, Xm, and Y is equal to XW, having slope L dash M divided by G dash M plus 1. So the equation 12 applies to all trays of the stripping section, such that the line on the enthalpy diagram from G-NP plus 1 to delta W intersects the saturated liquid enthalpy curve at L-NP, where G-NP plus 1 represents the vapor leaving the reboiler and entering the bottom tray NP, and L-NP represents the liquid leaving the bottom tray. Then, vapor GNP leaving the bottom tray is in equilibrium with liquid LNP and is located on the tie line NP. And as we know, the vapor leaving the reboiler is in equilibrium with the residue, hence the reboiler also shows an equilibrium stage, which is shown by tie line B in the diagram. As we already know, if we don't have XY data to draw the equilibrium curve in the composition diagram, we can project tie lines and we can draw the equilibrium curve. Then, if we draw random lines through delta W, and when we project their intersections with the HGY and HLux curves on the composition diagram, we get points like T, and after the jointing of these points we get the operating curve. Now we can draw trays and calculate the number of trays by the usual step construction method like the McCabe-Thiele method. Hence stripping section trays can thus be determined entirely on the enthalpy diagram by alternating construction lines to delta W in tie lines, and each tie line accounting for an equilibrium stage, and on the composition diagram we can use the step construction method. So that's all about Ponchon Savarit method for stripping section. And this is the second part of this video. Please click the link which is given in description box for first part of this video. In the third part of this video, we will discuss the Ponchon Savarit method for complete fractionator. So keep watching. If you like my video, please like, share, and subscribe to my YouTube channel, which is Chemical Adda.